In this video, we will introduce the state estimation function in PowerFactory. Study Case 1, undisturbed measurements should be activated. This network model represents a small distribution system at 3 voltage levels. We can see that there are a number of loads at 20 kV and at 0.4 kV. There are no generators in this model, just a single external grid supplying active and reactive power. The state estimation function is used to obtain consistent load flow results based on measurements which have been imported into PowerFactory, for example branch flows and busbar voltages. The states to be estimated might include the active and reactive power of loads and generators, and the tap positions of transformers. At the core of the function is an optimization process, whose objective is to minimize the difference between the calculated load flow results and the measurement values, through adjustment of the relevant element attributes. The state estimation function then provides the user with detailed reporting, which can be used to identify areas where improvements are required, because the measurement results are insufficient, or of poor quality. Let us first look at the input data and parameters. Starting with load objects, and looking at the state estimation tab, we see that both the active and reactive power are to be estimated. Likewise, the tap positions of a number of transformers. In a PowerFactory model, measurement devices can be created where elements are connected, and this project contains many such devices, which have already been populated with measurement data. The network graphic can be colored according to measurement locations, and here the red coloring indicates the presence of measurement devices. All the busbars and other terminals are colored blue, because the voltage measurement devices in the model are currently marked out of service. In this first study case, we will look at the state estimation in a rather idealized situation, where good quality measurements are available throughout the network. The state estimation command is found in the additional functions toolbox, here. The plausibility check can be used to detect obvious errors in the measurement data. We do not need to select it in this case. The observability analysis step is used to detect regions of the network for which insufficient data are available, or bad measurements are detected. This should be selected, with the option shown here. Before executing the calculation, let us first run a load flow, and observe the results, for example at this line end. Now the command can be executed. Information about the analysis appears in the output window. No problems are indicated. The results that we see here are very similar to those of the initial load flow. Note the green coloring throughout the graphic, which indicates redundant measurements. This means that there are more measurements than the minimum required. But such redundant measurements are still used, because they generally improve the quality of the state estimation result. No bad measurements are detected. Now let us activate study case 2, disturbed measurements. In this study case, the measurement data is more reflective of reality, with some measurement values being suspect. This can be for various reasons, including faulty metering or synchronization issues. This is where the plausibility check becomes useful, as it provides a means of discovering measurements which are clearly erroneous. Such implausible measurements will be ignored for the purposes of the actual state estimation calculation. For example, a power flow measurement should be ignored if the circuit in question is switched out. We execute the command. Looking in the output window, we can see that the plausibility check has detected some implausible measurements that are to be ignored. For example, 2 measurement devices failed the test of having non-zero flow on an offloaded circuit. Details can be seen in a network model manager. The locations of the devices can be marked in graphic. Once the plausibility step is completed, the observability check and the state estimation are run in turn, in an iterative process. Each iteration allows bad measurements to be detected and replaced by internally calculated set points. These bad measurements, which differ from the estimated values beyond the required threshold, are listed at the end. In the graphic, the coloring indicates whether bad measurements have been detected. The user can now examine each of these cases and decide whether it is possible to improve the quality of the input data, or live with the inaccuracy. After working on the input data and making use of the various options within the state estimation command, the user will reach a point where the estimated state is now considered acceptable. It is then possible to write the data back to the database and save it as a new operation scenario, to use for further network analysis. Now let us look at study case 3, unobservable network. In this study case, many of the measurement devices have been marked out of service, to illustrate a situation where the measurement data is patchy. Looking at the coloring of the graphic before the calculation is run, we can see from the number of elements now colored blue, that many parts of the network do not have measurement information. In this instance, the observability analysis step is particularly important. We execute the command. Again, a number of bad measurements have been detected. In addition, we can see from the output that unobservable states have been detected. The user will now have to decide what actions need to be taken to improve the quality of the input data. In this case, the introduction of additional measurement locations may be required. The PowerFactory state estimation function is mainly used in the context of automated processes. For example, as a custom development, it can be integrated with the user's own SCADA systems.